Hello friends, good morning all of you. Here I am Gadekar Sachin Pandit. Today we are discuss about crystal radii, trends in crystal radii, covalent radii. Okay, so last lecture we are discuss about atomic and ionic radii. Okay, so in which we are discuss a covalent radii, ionic radii, and then covalent radii, metallic radii, and van der Waals radii. Okay, so in which van der Waals radii is more than metallic radii. Metallic radii is more than covalent radii. It is the trends of atomic radii. Okay, so today we are discuss on crystal radii, trends in crystal radii, covalent radii. Okay, so first we discuss here crystal radii. Here, what is the crystal radii? Crystal radii is one half of the distance between nuclei of two adjacent atoms in a metallic crystal or metallic lattice. Half distance between nuclei of two adjacent metal atoms in a metallic crystal lattice is called crystal radii. Crystal radius is the actual radius of polyvalent ion in the crystal. Okay, so first you know the different terms such as univalent radii, monovalent radii, polyvalent radii, crystal radii. Okay, so these terms is most important. Okay, what is the univalent radii? Univalent radii, it means single. Monovalent means single. Univalent radii is the example of NaCl. Okay, so in which Na positive, it means lose one electron. It is a univalent atomic radii. Okay, ionic radii. These sodium plus ionic radii is the near about or same, equivalent, and univalent radii of sodium ion is observed and calculated are same. Okay, so similarly chlorine ion. Okay, so chlorine ion, it means gain one electron to form say chloride anions. Okay, negatively charged ion, these are also univalent or monovalent ions, and its radii is called monovalent radii. And these chlorine negative charge ions observed and calculated ionic radii are same or agree with its calculated and observed. But in polyvalent ionic radii, there are different calculated and ionic radii. Okay, so that's why we have to need a crystal radii. Okay, so polyvalent means more than two valent ions. Okay, more than two valent ions. Okay, so called polyvalent ionic radii, and they polyvalent ionic radii converts to crystal radii, then we get a similar radii, means calculated and observed radii are equal and they agree. Okay, that's why we have to need a crystal radii. Okay, if we convert polyvalent radii into crystal radii and then calculate, it means observed and calculated values are equal. So we have to need a convert crystal radii. Okay, polyvalent radii into crystal radii, and terms in all univalent, monovalent, polyvalent, and crystal radii. There are different four terms. Okay, So here crystal radii. Crystal radii, it is monovalent atoms in if monovalent atoms observed and calculated radii are same or equal or agree with observed and calculated radii in monovalent atom, but in polyvalent ions in which observed and calculated radii are not same or not equal or not agree with calculated and observed radii. Okay, so that's why we have to need a converse crystal radii. Okay, so in polyvalent radii, how can calculate crystal radii? In polyvalent ionic radii, we can calculate if the ionic radii of polyvalent ions can be calculated by assuming that polyvalent ion behave as univalent and there is no change in electronic configuration. At that time we can calculate a crystal radii. Okay, so monovalent or univalent radii. Univalent radii, suppose Na plus means sodium metal ion radii are equal observed and calculated. This is the univalent radii. But in polyvalent radii, there are observed and calculated value are different. That's why they converts behave as univalent radii like sodium metal ion and there is no change in electronic configuration. At that time we can calculate a crystal radii. How can calculate or how can convert crystal radii, polyvalent radii into crystal radii? Okay, so here one more example of polyvalent ions of magnesium oxide. Okay, so in this magnesium oxide in which observed and calculated ionic radii are different. Okay, so if we calculate its ionic radii in crystal radii, okay, so at that time there are different. First, in magnesium oxide consist a Mg2 plus charge and O2 negative charge. Okay, so univalent radii of magnesium 2 plus is equal to 0.82 angstrom. Similarly, oxygen 2 negative charge, univalent radii of O2 minus is 1.76 and it gives a 2.58 angstrom. Okay, this is the calculated ionic radii of magnesium oxide, but observed is 2.05. Calculated and observed are not equal in magnesium oxide. Calculated is the 2.58 angstrom and observed is the 2.05 angstrom. Okay, so these observed and calculated ionic radii of magnesium oxide is not equal. So that's why we have to need magnesium oxide polyvalent ionic radii converts to univalent radii or crystal radii. Then observed and calculated radii are equal. They are agree with observed and calculated. So next example, calcium oxide. Similarly, in calcium oxide, here a calcium 2 positive charge and oxygen negative charge combines to form a calcium oxide crystal and its ionic radii is different, calculated and observed, in which calcium oxide in which univalent radii of calcium 2 plus is 1.18 angstrom. Similarly, univalent radii of O2 minus in calcium oxide is 1.76 angstrom. So calculated its value 2.94 angstrom. Okay, so in calcium oxide calculated radii 2.94, but observed radii is 2.39, less than calculated radii. Okay, so that's why calcium oxide is polyvalent ions converts to the univalent radii or crystal radii. So that's time we have to calculate a accurate radii of calcium oxide. So that's why we have to need a polyvalent radii converts to crystal radii. Okay. So calculated and observed value are not match of magnesium oxide as well as calcium oxide. It is a one more example. Okay. So in which calcium 2 positive charge, magnesium 2 positive charge, oxygen 2 negative charge are not univalent, they are bivalent. That's why these ionic radii are not match or are not agree with calculated and observed value. So that's why we have to need it converts a crystal radii. Okay, so how can calculate a crystal radii? How can convert a univalent radii, polyvalent radii into univalent radii? Okay, so in this slide, how can they can be calculate univalent radii? Okay, so it is possible to convert the univalent radii of the polyvalent ions into their crystal radii. How can calculate crystal radii? Okay, so it is possible to convert the univalent radii Ru of the polyvalent ions into crystal radii. So that's why we have to need a understand Born equation. Okay, so crystal radii we can calculate by using Born equation. Okay, what is the Born equation? Born equation is crystal radii is equal to univalent radii into Z square minus 2 into n minus 1. Okay, so here R crystal means crystal radii and Ru is univalent radii and Z is the charge on ion and n is the cell constant or Born exponent. This n is depends on a metal belongs to the which types of period, where its position in period. Okay, so they may be first period, they may be second period, they may be whatever may be. Okay, so in Born equation crystal radii we can calculate. Okay, crystal radii is equal to univalent radii into Z minus 2 in bracket n minus 1, where Z is the charge on ion, n is the cell constant or Born exponent. Okay, so this Born exponent is in right hand side types of cell elements or configuration. Suppose our ionic radii, okay, so belongs to the helium period. In helium at that time Born exponent is equal to 5. So ionic radii belongs to near about in period neon family. So at that time Born exponent is 7. Then ionic radii belongs to argon family. At that time its Born exponent or n near about 9. It belongs to krypton family. At that time n is 10. Then xenon belongs, ionic radii belongs to xenon family, then n value is equal to 12 or Born exponent is 12. Okay, so this is the periodic table in which helium, neon, argon, krypton, xenon is the period first period, second period, third period, fourth period, sixth period, etc. Okay. So ionic radii belongs to which periods? Okay. Suppose oxygen. Oxygen has a 16 group element. Okay. Suppose oxygen gain 2 electron to form say O2 minus, and they belongs to neon family or neon groups. At that time we use a Born exponent is 7. Okay. If suppose example of lithium, lithium lose one electron to form say lithium plus ion, and this lithium plus ion electronic configuration belongs to helium like, and helium like at that time we use n value is equal to 5, like this. Helium, its Born exponent is 5. If ionic radii belongs to neon family, at that time n value or Born exponent we use 7. Okay. Here suppose a potassium, first group element left hand side, potassium lose one electron to form say potassium positive charge. Similarly calcium, calcium lose 2 electron to form say calcium 2 positive charge, and it belongs to argon family. Okay. So argon family, its Born exponent is 9. Okay. So n Born's exponent argon is equal to 9. Okay. Similarly here now calculate the crystal radii of magnesium oxide by using Born equation. Okay. So calculate the crystal radii of magnesium oxide by using Born equation, in which a given such as univalent radii of magnesium oxide is 0.82 angstrom and O2 minus is equal to 1.76 angstrom. So now calculate the crystal radii of magnesium oxide by using Born equation. What is the Born equation? Born equation is crystal radii is equal to univalent radii Ru into Z charge on magnesium oxide, then square of minus 2 in bracket n minus 1. Okay, this is the Born equation. First case, for calculation crystal radii of magnesium oxide by using or converts univalent radii, where magnesium oxide Z is the 2 because 2 positive charge on magnesium. Suppose in which what is the n value of magnesium? Magnesium here, magnesium belongs to alkaline earth metals, in which second group element, it is a third group, third period of elements. These magnesium lose 2 electrons to form say it's near about neon family, and neon family its Born's exponent Ne is equal to 7. That's why here we use n equal to 7 in first equation for Mg. N equal to n equal to 7. Why? Because n is the Born exponent, and Mg, if 2 electrons lose to form say neon family. Okay. So similarly we calculate crystal radii of magnesium 2 positive is equal to 0.82, it's given, okay, into its charge 2 square 2 in bracket 7 minus 1. 7 is the magnesium 2 plus belongs to the neon family. That's why it's a Born exponent 7, and then magnesium oxide radicals is 0.65 angstrom. It is a calculated. And second, for O2 minus, Boron exponent crystal radii of O2 minus is where Z is the O2 minus means 2 negative charge, that's why Z is 2. Similarly, N equal to 7. Why? Because in this oxygen gain 2 electron to form a neon inert element configuration. So that's why we have used a N equal to 7, and this N equal to 7 is Bohr exponent. Okay, so univalent radii of oxygen 2 minus is 1.7 angstrom. So calculate crystal radii O2 minus by using this. Put the value of Bohr equation 1.76 angstrom into 2 square minus 2 into 7 minus 1 equal to 1.40 angstrom. So observed radius of magnesium oxide is equal to equation first and second. Put the value first and second. 0.65 plus 1.40 is equal to 2.05 angstrom, and this 2.05 angstrom crystal radii is equal to the calculated radii. So it is equal to both observed and calculated, or agree with observed and calculated radii. So that's why we have to need a converts polyvalent radii into univalent radii, and univalent radii we calculate by using Bohr equation. Okay, so here trends in the value of crystal radii. Trends in the crystal radii. It is difficult to establish a trends in crystal radii because of it depends upon several factors. Trends in the crystal radii is difficult to establish. Why? Because it is depends upon several factors. So many factors are affected on crystal radii. So that's why not we are explain properly trends in crystal radii. When atoms or ions are present in bulk materials, many factors are affect their size and radii. Okay, so there are 4 factors are affected in crystal radii. First is the bond order. Okay, so there are different types of bond order. Bond order 1, 2, 3, 4, 1, 2, 3, okay, etc. So these bond order are also affect on crystal radii. Suppose in carbon bond order is 1, at that time different crystal radii. If bond order is 2 means alkene group, at that time it's double bond. Okay, so it gives a different radii. If bond order is 3, carbon triple bond carbon, it is bond order 3, at that time its crystal radii are different. Single bond, double bond, triple bond, increasing the bond order decrease the crystal radii. Okay, so that's why this is depends on bond order. Similarly, it depends on oxidation number. Okay, lower oxidation number and higher oxidation number. Okay, so lower oxidation number is the higher bond or higher the crystal radii, and higher the oxidation number, it's lower the crystal radii, because its outermost shell electronic configuration change in oxidation number. Okay, similarly degree of ionic and covalent character also affect in trends of crystal radii. Degree of ionic and covalent character. Okay, so covalent and ionic character are also affect in crystal radii. And then repulsive forces between atoms. Suppose positive charge ions, at that time repulsive forces is greater than positive negative ions is the attractive forces. That's why its change crystal radii. So positive negative attracts tightly hold atom or ions, so that's why its crystal radii are different. So there are four factors are affect on crystal radii. First is the bond order, second is oxidation number, third is the degree of ionic or covalent character, and then fourth is the repulsive force between atoms. Okay, so now one more examples of calculate the bond or calculate the crystal radii or radius of atoms. First example, what is the covalent radius of fluorine in CF, means carbon fluorine bond? What is the covalent radius of fluorine in carbon fluorine? The distance of carbon is 1.4 angstrom and covalent radius of C is carbon is 0.77 angstrom. Okay, here given carbon fluorine bond distance 1.4 angstrom and carbon radii is 0.77 angstrom. So fluorine radii, calculate the fluorine radii is equal to carbon fluorine minus carbon radii. Okay, 1.41 minus 0.77 is equal to 0.64 angstrom. Okay, so this is the simple equation for calculate the one atom's radii for given two value. Okay, first bond and second is the one atom, then calculate the third components. Okay, so next is the covalent radii. What is the covalent radii? Covalent radii in metal, there are different covalent radii, metallic radii or ionic radii. So there are different types of radii. First of all, we will discuss on metallic radii. Metallic radii, metal atoms are bonded together are called metallic bond. Okay, metallic crystal in which metal atoms are bonded together are called metallic bond. Okay, so non-metals, similarly covalent bond. Okay, non-metal crystal, non-metals are bonded together their atoms, non-metals. Suppose carbon, carbon connected with carbon, carbon connected with silicon, etc. These are the non-metals. Non-metals are bonded together, their bond are called a covalent bond. Okay, carbon carbon is a covalent bonds. Okay, so next is the covalent radius. Okay, so covalent radius is the internuclear distance between the two atoms. They may be similar atoms or they may be dissimilar atoms. Okay, so covalent radius is the distance between nuclear distance between two atoms. Okay, so example, covalent radius of carbon is 0.77 angstrom. Okay, so covalent radius of silicon is 1.717 angstrom. Okay, so now carbon silicon atom. Okay, so carbon connects with silicon or carbon reacts with silicon to form a carbon silicon bond, covalent bond to form a carbon silicon, and its bond length, covalent radius of covalent bond length is equal to 0.77 plus 1.17 is equal to 1.94 angstrom. Okay, so carbon silicon bond length is 1.94 angstrom. This is the good agreement with observed and calculated value. Okay, so this is the covalent radii. Okay, metallic radii, non-metallic radii, covalent radii. Okay, so covalent radii of carbon is 0.07 and covalent radii of silicon is 1.17 angstrom, and they addition together to forms a carbon silicon, and its bond length is 1.94 angstrom, and this is good agreement with observed and calculated value. Okay, so now we are stop here. Then next lecture we are discuss about the ionization energy. Okay, so ionization energy or ionization potential, then trend in ionization potential in periodic table. Okay, so then electronegativity. These 3 points we are discuss on next lecture. Ionization energy or ionization potential, trends in ionization energy in periodic table, and then electronegativity. These points we are discuss on next lecture. Okay, so now we are stop here. Thank you for watching this video. Thank you all of you. Have a nice day.